Good day, everyone. My name is Bruce Scruggs, and I'm going to be talking about using the EDAX Orbis Micro XRF Elemental Analyzer to analyze forensic samples. I'd like to start by saying a few words about what kind of results do we get using X-ray fluorescence. X-ray fluorescence provides information on elemental composition. This can be both qualitative information, looking at the intensities of various elemental peaks. It can be quantitative information, where that may be all the way using specialized computer models to calculate weight percent compositions, or more simplified models simply to calculate ratios between elements. For layered samples, you can measure multilayer thickness and get composition information as well. This is typically used more in the industrial sector. What small spot and microspot XRF brings to this sort of analysis is that you can measure small fragments where the X-ray optics concentrate X-ray excitation onto the small fragment so that you get better sensitivity for those small fragments, or you can measure larger components and look at the distribution or homogeneity of some elements on that larger component. Here are some of the advantages of an XRF analysis. The technique is non-destructive. We use roughly 50-watt X-ray tubes in our equipment. There's no beam damage to the samples. There's no need to coat the sample to make it conductive. Many types of samples can be measured as is. So this is important in being able to take that sample and then measure it in other other analytical techniques, as well as minimizing sample preparation. It covers most of the periodic table from sodium to berkelium. The analytical range can be from 100% down to parts per million. X-rays are penetrating depending on the sample matrix and the energy of the X-rays that you're measuring. You can go from microns to millimeters. This is most important when you want to do things like coding analysis. The technique can be done in a rough vacuum, maybe down to 300 millitorr, or it can be done in atmosphere. The difference between these two is it affects what range of light energy elements that you can measure. So in vacuum, you might typically measure down to sodium. And also, this type of instrumentation has a video microscope, so navigation is done by the video microscope image. The Orbis Micro XRF Elemental Analyzer is used in the forensics laboratory to examine trace evidence. We are looking at some characteristics of the elemental composition of that trace evidence to draw some conclusions relevant to a crime or an accident. Some of the specific kinds of goals, we would compare trace evidence found at a crime scene to evidence found elsewhere to see if there's consistency or inconsistency between that evidence. We would look to validate trace evidence against the way the crime scene is laid out, the alibis that are given by various suspects, or, for example, the marketing of a product that's being sold. Is it consistent? Is that product consistent with the product marketing? You might also validate some sort of evidence or product against known manufacturing methods. This could be an example of situations of counterfeiting. It's also an excellent tool for screening evidence for further analysis that may be time-consuming or more expensive or even destructive, because this method is non-destructive and it's relatively fast to use. I want to discuss a little bit the theory of the spectroscopy so that you have a later understanding of what was actually being measured in this technique. Here's a simple Bohr's model for an atom. You have the nucleus surrounded by various orbital shells of electrons. We use X-ray excitation in XRF to excite the sample. And by exciting it, we have incoming X-ray photons with a greater energy than the binding energy of some orbital electron. That interacts, exciting the electron and ejecting it. A vacancy is created. We may have some residual X-ray photon created that could go off and do something else in the sample matrix. We now have a high energy state here. And electrons in higher energy shells are going to relax to fill that vacancy. In the process of relaxation down to the lower energy state, we are going to potentially fluoresce an X-ray photon, and the energy of that X-ray photon is characteristic of the element that you're measuring. When a vacancy is created in the K shell, the transitions that go down to that K shell are called the K-line series. When you have a vacancy created in the L shell, those are transitions that are the L-line series, and when you have a vacancy in the M shell, that's termed the M-line series. So in X-ray fluorescence, we're using X-ray excitation to create electron transitions in the orbital shells, and these produce characteristic X-rays. The characteristic X-rays have specific energies which identify an element. Heavier elements have a more complicated electron orbital structure and can produce multiple characteristic X-ray series. Allow me to show you a couple of examples of what the X-ray line series look like. This is the iron K series. On the left you have the K alpha lines, and on the right you have the K beta lines. The K beta lines are a little higher in energy than the K alpha lines. The K alpha lines are approximately about 5 times more intense than the K beta lines if there aren't any matrix effects involved. This is the L series for lead. It's typically this sort of characteristic quadruplet. You have the L alpha line, which is the most intense line. Then in the middle there you have the L beta line series off at around 15 kV. At the highest to the right is the L gamma series, and then you have a smaller line low in energy below that L alpha line. So to summarize, XRF is an atomic spectroscopy. It measures the presence of an atomic element. When we talk about composition, we're referring to the elemental composition, not to the molecular composition. And the information that we get about elemental composition, we could be using computer modeling to give you weight percents, or we could be using something as simple as elemental ratios to make comparisons between different samples to say, are they consistent with one another or not? This is the Orbis Micro XRF system. It has a vacuum chamber, so we can make analysis both in vacuum, or we can turn the vacuum pump off and you can make measurements at atmosphere. X-ray excitation is done with a 50 kV, 50 watt X-ray tube, so it's about the same power as an incandescent light bulb that you would have around the house. It's air-cooled, so there's no user maintenance necessary for the X-ray tube. It employs focusing and collimating X-ray optics. Focusing X-ray optics concentrate the excitation down onto small sample fragments, so we can get very good sensitivity on small fragments. Collimators are made by drilling a hole through an X-ray beam stop, and we do this to create larger analytical areas so we can get an average analysis of a larger amount of material. We have a digital video system in the Orbis to image the sample and also to navigate around on the sample to make decisions on where to analyze. There's an XYZ stage. The detector is a silicon drift detector. It's electrically cooled, so there's no need for user maintenance on that either. I wanted to explain some of the design features of the Orbis system and why we choose to put these features in there to make an XRF analysis. The Orbis has a coaxial X-ray and video geometry system. What does that mean? So we look at the cartoon here, and we want to analyze that blue spot on a sample. In the Orbis design, this axis, the gold dotted arrow, represents the view of our video camera. Our X-ray analysis shares that same axis. The X-ray analysis is represented by the maroon arrow. In a non-coaxial design, we want to look at that same blue spot. The camera looks straight down at that spot, but the X-ray excitation comes in at an oblique angle. When you have a non-coaxial geometry, the X-ray path is not the same path as the video. So when you're looking at the sample, you cannot visualize the X-ray beam and the path that it's coming in to actually excite the sample. And this, in certain scenarios, leads to analysis error. Here's a situation where we want to look at a sample, that blue spot. And it's represented here in the cartoon. The sample has some topography to it. There's a block on the sample of some kind. In the non-coaxial geometry, the video is looking down at that spot we want to analyze. The X-ray beam is coming in at an angle. Because we can't visualize the X-ray beam in the video path, you don't really know whether you're hitting that blue spot that you want to analyze or you're hitting that topographical feature where the starburst is. You're going to get a signal one way or the other, but you're not expecting to analyze where the red starburst is. With the Orbis system, the X-ray and the video are coaxial. So that means that in the video image, you can see the path the X-ray beam is going to take to the sample. That has a very positive benefit. Here we have the same blue spot topographical sample that we want to analyze. In the Orbis coaxial design, the video is looking at that blue spot. If I have a clear path to the blue spot, then you can see that my X-ray beam also has a clear path to that spot, and it's not obstructed. I'm analyzing the blue spot. I know where the X-ray beam path is. This is another sample scenario where having a non-coaxial design can lead to analysis error. I have a different kind of a sample now. I have a piece of plastic, a piece of glass, something along these lines, and I have an inclusion embedded in there that's represented by the little blue cube. And I want to analyze that little blue cube. But there's no reason to expect that there's only one inclusion in there. Maybe there are more inclusions in that sample. And I want to go and I want to measure different inclusions and know that I've actually had the beam measuring a specific inclusion. In a non-coaxial design, again, I have the video image coming and looking at the inclusion that I want to measure. But the X-ray beam doesn't share the same path. And so what happens is I end up measuring the wrong inclusion because I can't see the X-ray path in my video image. With the Orbis coaxial design, again, we have that same sample with the two inclusions. I want to measure that blue inclusion, so I have the camera system targeting that the blue inclusion. And because I can see the path to that blue inclusion, I know my X-ray path is the same, and I'm able to measure with confidence. I know I'm measuring that blue inclusion rather than having the beam obstructed by something else, such as the red inclusion off to the side. So with the Orbis coaxial design, where the X-ray path is observed in the video, here's a couple of different sample scenarios where I know when I'm looking at that inclusion in the sample, or I know I'm looking at that spot on the topographical sample, I can measure with confidence with the coaxial design in the Orbis. I know I'm hitting that part of the sample. With the non-coaxial design, I'm never really quite sure whether I'm measuring the right spot or not. I want to discuss now the perpendicular geometry of the Orbis. So in the Orbis design, the analytical beam is perpendicular to the sample surface. The benefit here is that there's no shadowing of the X-ray beam. If you can see the sample, you can analyze the sample. This sounds a little bit similar to the coaxial argument, but it's a little bit different. Again, when you have that perpendicular geometry in the Orbis, you look down, you can see the sample. You can also analyze the sample with the X-ray beam. In a non-perpendicular X-ray beam geometry, which is characteristic of the non-coaxial system, we have this same analytical scenario. We're trying to measure that blue spot. The non-perpendicular geometry thinks you're measuring at the blue spot. But with that oblique geometry, you're potentially not measuring at that spot. You're getting a signal at some other position on the sample. The X-ray beam has been shadowed, and there's no ability to detect that problem. So what happens is that in certain kinds of analysis, such as elemental imaging, this can create distortions in the elemental image. Here's a sample just to sort of demonstrate that. It's a hexagonal wire array on an underlying grid support. It looks flat. It has three-dimensional structure to it. But to any sample that may be flat, X-rays are penetrating. So many samples have some sort of three-dimensional structure due to the penetrating nature of the X-ray analysis. With the non-perpendicular X-ray geometry, let's say here I'm measuring this yellow area. I'm doing an elemental image of it. I'm collecting a spectrum at each point within that area, and then I'm going through the spectral database and mining out an elemental intensity. This is what the image of that particular area looks like. It's distorted because the underlying grid is distorted in the image. So what's happening there? Well, here's my sample. I've got some sort of grid. I have some underlying structure in there, and I'm trying to measure the blue dot area. In the non-coaxial system, the system thinks that I'm at the camera position. I'm looking at that blue spot. But the X-ray beam is coming at an oblique angle. So I'm measuring that sample in a different position. In this particular case, the beam is penetrating into the material, hitting the side wall of that particular structure or whatever is buried in the sample, and giving me a signal someplace else. And that's what leads to these distortions in the elemental image for a non-coaxial system. So now let's take a look at that same elemental mapping scenario with the Orbis system, with the perpendicular X-ray beam geometry and the coaxial alignment of the X-ray beam and the video camera. There's the sample that we're measuring. We're measuring that exact same area. And you can see when we make an elemental image of that area, the elemental image is a correct representation of the sample that we're looking at. Why is that? Because here's again our same cartoon. The Orbis system is targeting in the camera position that blue spot, and the X-ray beam, because it's perpendicular, because it's coaxial with the Orbis video, we are indeed measuring at that blue spot. So we get a true image. One last point about the perpendicular X-ray geometry of the Orbis system. Another benefit of this is that there is no exact fixed analytical plane for where the sample has to be measured in order to accurately target the sample. So what do I mean by that? Here we are, there's our sample. We're trying to measure that blue spot. In the Orbis perpendicular geometry, the camera is looking at that blue spot. The X-ray beam is hitting the blue spot. Well, let's say that the operator of the system hasn't exactly positioned the sample correctly. Maybe it's a little bit high, maybe it's a little bit low. But it doesn't matter because the camera is still looking at the exact same spot, and the X-ray beam is still hitting the sample in the same position. In the non-perpendicular geometry, we're trying to hit that spot. The camera is looking at that spot. The X-ray beam, when the sample is at the correct height, is correct. But if the technician was in a hurry, they didn't make the exact adjustment of the sample height, maybe the sample is a little bit too low, they make the analysis anyway. Now with that non-perpendicular geometry, the beam is not measuring the sample in the place that the camera is reporting. So you have an error in the analysis. The Orbis uses a patented turret design which houses both the X-ray optics and collimators and the lens to the video camera. So you can view the sample with the video camera, and then when you want to go ahead and analyze, the system automatically puts into position whatever the selected X-ray optic is and makes that analysis. The benefit here is that we can have a variety of different X-ray beam sizes using the same set of filters and the same X-ray tube to measure, to tailor the analysis to whatever the feature is that you're trying to measure. So if you're trying to measure a single fragment, this little blue cube, you would use maybe the smallest focusing X-ray optic that you have. If you have some larger bit of sample, you would choose a larger collimator to give an average analysis for that little pile of sample. If you had a much larger sample, you would, let's say, change to the largest collimator to give an average measurement of that larger sample. So you can tailor your analysis based on the kind of sample or based on the kind of analysis that you want to do. The Orbis system also has a primary beam filter system. What are primary beam filters? So these are thin pure metal foils. They're positioned in the excitation beam line. And you can tailor your analysis using different filters to condition the exciting beam. What's the benefit? You can improve the sensitivity of your measurement over a specified spectral energy range. Or you can, for example, filter out the tube target lines. As an example of that, you could analyze chlorine in the presence of a rhodium tube where one of the rhodium tube lines might normally overlap the chlorine line. You can use the filter to filter out the rhodium tube line and get a clear analysis of the chlorine in the sample. I want to take a moment to point out one of the benefits of the Orbis filter design. It's important to note that the filter system is a scattering element, and in a Micro XRF system you have a focusing component. So it's important to put the scattering element first, then the focusing component, so that your beam's not scattered on the sample. So here I show you sort of the beam line of the Orbis design. You have the bright gold X-ray beam coming out of the X-ray tube. It passes through a filter in the filter wheel. There are multiple filters there. So the beam is conditioned there. There's some potential scattering going on there. Then you have the focusing X-ray optic, which takes that, potentially a little bit of scattering of the X-ray beam, and it simply focuses down onto the sample, so that there's not a perturbation of the scattering element on your analysis. In an incorrect design, you have the X-ray beam coming out of the X-ray tube. It goes into the X-ray optic, focuses the beam down onto the filter, and then that focused beam passes through the filter. There's some scattering involved there. So you have the main component on the sample, but you also have some scattered X-ray giving you an analysis outside of the area that you think you're analyzing. So again, you don't have the sample correctly targeted in this sort of a design where the scattering filter wheel is after the focusing element. Now I'm going to be discussing some applications of the Orbis system to measure forensic samples which you may encounter in your laboratory duties. The first example is glass analysis. Glass is a very common trace evidence found at the crime scene. Glass is in all kinds of different products, window glass. Various household items are composed of glass, automotive glass, the windshields, the the windows, the headlights, container glass. Glass is sort of the ideal trace evidence because it's durable, it breaks into small parts, small fragments. It can get onto a suspect's clothing and transfer onto the suspect's clothing, and they carry it away from the crime scene. And it's durable. The composition doesn't change over time. The goals in glass analysis are to, say, identify glass types, whether it's window glasses versus container glass, to compare glass fragments found at a crime scene to glass fragments found on a suspect's clothing, to use glass to verify the consistency of the crime scene investigation, the scenario surrounding what supposedly went on at the crime scene. The advantages of using the Orbis XRF system for glass analysis. Again, it's non-destructive. There's no beam damage. There's no pretreatment that you have to use on the sample, no coating. You can measure the glass fragments or the glass parts as is. You can get good sensitivity on elements from around sodium to berkelium. You can automate the data collection on multiple fragments. And because of the design features that we spoke about before in the Orbis, you can target those fragments accurately. Because this sort of analysis is non-destructive, it allows you to first use the Orbis to make measurements on the glass, and then you can decide what other methods you might want to use to measure that glass. For example, you might want to measure color, refractive index, and density to get a full characterization of the glass fragment for later use in comparing to, say, fragments between what's found at the crime scene to fragments that might be found on a suspect's clothing. So this is an example characterizing the glass type. We're comparing two spectra from two different glass fragments. The red outline spectrum is a typical container, a bottle-type glass. The blue outline spectrum is a typical flat glass. That might be like a window glass, for example. You can see in the container glass where the red arrows are marked that it has lower levels of magnesium and iron. And that the window glass has elevated levels of magnesium and iron. So these are characterizations that can help you to identify the glass type. You'll also note here that there are some other differences in the spectra. You can clearly see that there is a potassium peak in the container glass at around 3.3 kV. You can also see the more intense strontium and zirconium lines at around 14 and 16 kV respectively for the container glass. Now the strontium and zirconium lines are typically reflective of the impurities that get into the glass during the manufacturing process. These elements come from the refractory brick lining the furnace. Window glass fragment comparisons now have a standard test method associated with them. So what they're doing in this standard test method is that they are looking at window glass found at a crime scene, and they are comparing it to glass fragments that might be found on a suspect's clothing. And this was such an interesting forensics analysis in the United States that a group of the forensics laboratories and some universities got together and developed a standard test method for this. It's ASTM method E2926-13, standard test method for forensic comparison of glass using micro X-ray fluorescence spectrometry. I think the first published issue went out in June 2013. In this type of comparison, a full quantitative analysis getting weight percentages of elements in the glass is not typically done. And the reasons why that is they saw too much variation of the weight percent composition based on the surface topography of the fragment or variations in fragment thickness. So instead what they use are elemental ratios. So they have about 6 characteristic ratios for window glass, but you can use any set of characteristic ratios that you want for any type of glass that you're making comparisons for. And they will ratio certain elements together to minimize the effects of topography and thickness. And they will then compare those ratios between the fragments found at the crime scene to those fragments found on a suspect's clothing to decide whether the fragments are consistent with one another or not. I got interested in taking a look at the ASTM methodology for the window glass fragment comparisons, and I had some ideas about what could be done to improve the methodology for that method. So what I had done studying some bottle glasses, for example, which were readily available at the grocery store, was to make more than one spectral acquisition of the fragment under different filter conditions. So I might use, say, one filter to highlight the traces of iron or zinc or strontium and zirconium in the sample. And then I'd make another acquisition without a filter to highlight the lighter element series, the sodium, the magnesium, aluminum, that kind of thing, and combine the intensities from those two acquisitions. And that had two basic benefits to it. It improved the sensitivity of the analysis because we were using some filtering, and it also eliminated spectral artifacts. So for example, if you had the tube line scatter in the spectrum and you were using a rhodium tube, but you wanted to measure for chlorine as well, then if I used a filter, I could knock that tube line out and be able to use the analysis for, say, chlorine or sulfur as well in this type of a comparison. There's a couple of presentations that I gave at the Denver X-ray conference last year in 2015 and also this year in 2016. These presentations are published in the conference proceedings, which are called the Advances in X-ray Analysis. I wanted to show you a plot of how one of these ratio comparisons is made. So I took some of the data from one of these presentations that I'd given. And what I was doing here was analyzing the same brand of soda bottle from different time periods and from different continents. So I had 3 different bottles, one that was bottled in Mexico in 2011. The Coca-Cola in the United States, you can buy it bottled in Mexico because they use pure cane sugar as opposed to high fructose corn syrup. So I got one bottle bottled in 2011, another bottle bottled in 2015, and then I was in Germany at one point and got a Coca-Cola bottle there in 2015. So this is a plot of 2 fragments from the 2 bottles from Mexico and 3 fragments from the bottle in Germany. And we make several different measurements on each fragment. And in this case, I'm plotting the iron to lead ratio. There's roughly around 50 to 100 parts per million of lead that I found in this bottle glass, lead oxide. And so each tier of the plot here shows you the results for one fragment. And if you have an overlap between these replicate measurements, then you can consider the 2 fragments to be consistent with one another. So you can see the 2 fragments from the Mexico bottle 2011 are consistent with one another. However, there's a difference in the iron to lead ratio for the Mexico bottle from 2015. So you can see those 2 fragments are consistent with one another, but they're not consistent with either of the other 2 bottles. And you can see that the bottle from Germany was also inconsistent with the 2 bottles from Mexico. The real challenge here was to distinguish the 2 bottles bottled in Mexico at different time frames. The bottle from Germany had quite a bit of, had several differences in the basic elemental composition of the bottle, which you would expect because they're made on different continents. So I do not expect that they're shipping bottles back and forth across the Atlantic Ocean. Another application of the Orbis XRF instrument in forensics laboratories is looking at bullet projectiles and gunshot residue analysis. What we see over here on the right is an elemental map of a test bullet tear through a fabric, a gunshot through a piece of fabric. You can see in the center, this is the lead elemental map, and you can see in the center the very the heavy wipe the bullet against the fabric, and that leaves traces of the bullet wipe on the fabric, so you can tell whether that's a lead projectile or copper-jacketed projectiles will leave a copper wipe on the fabric. The second component of this is that you can see the gunshot residue spread out over the fabric. So you know this was taken at relatively close range because you have gunshot residue on the fabric itself. Now, you can analyze for all different kinds of gunshot residue. You can look at lead, antimony, barium, the typical gunshot residue. You can look at lead-free formulations. You can look at tagged formulations, formulations where different manufacturers will dope it with an elemental fingerprint. As long as the elements are within the detectable range of the instrument from sodium to berkelium, you can make measurements of the gunshot residue. You can also do blood stain patterns based on the iron content. You can look at different explosive residues as well, as long as there's something within the elemental range of the tool that you can look at. This is some example data done a few years ago looking at gunshot residue pattern analysis. And the goal of this was to sort of calibrate the shooting distance as a function of the intensity of the gunshot residue pattern. The more intense it was, the closer the shot was to the fabric. And so we show two plots here. There on the left is the lead L intensity of the gunshot pattern. And on the right is the zinc XRF intensity of the gunshot pattern. So basically this was in the range of about going from 10 centimeters out to about 1 meter or so. You could see that we get a pattern. The more intense the gunshot residue pattern, the closer the range of the shot. So the idea here is to be able to measure the pattern and get an idea of where the distance of the shooting took place using some test fires with maybe the weapon that was found at the crime scene, and then to determine if that if the data that comes from the test fires is consistent with the crime scene evidence and the alibi given by the victim. For example, you could tell whether the shot took place from a great distance or whether it was self-inflicted. This is an example using the Orbis XRF system to analyze paints and paint chips. Paint contains a lot of inorganic additives, and the composition of those inorganic additives might depend both on time. So paints used years ago might contain lead oxides in them, whereas paints used today probably would be some sort of lead-free formulation. Or it could be that it has an inorganic formulation based on whether it's for interior use or for exterior use. So here's an example of a paint chip that I found on the Seattle Sound ferry. That's one of the ferry boats that runs in the Seattle Sound. That's on the west coast of the United States. This particular chip was rather thick. It's almost a millimeter thick, and I was surprised to find that it had about 12 layers in it. So I decided to put it into the system and analyze a few of the layers. And so what I found really interesting about it, I've marked 2 of the layers that I analyzed, the layer labeled with a 5 and the layer labeled with a 7. And you go and you look at the spectrum on the left, and you can see layer 5 is the red spectrum, the solid red spectrum. Layer 7 is the blue outline spectrum. Layer 5 contains lead. You can see that that lead L quadruplet that we were talking about earlier, running from about 10 kV up to 15 kV. There's the alpha, beta, and gamma lines of lead. When you look down at some of the later layers, layer 7, you can see that all the lead is gone, and at this particular point it's more, you see an increase in the titanium. That's the blue outline peak at around 4.5 to 5 kV. So I'm making an assumption here that the time sequence on this chip, it runs from right to left, so where right are the earlier layers of paint, and as you go to the left, you get to the later layers of paint, because I'm assuming at some point they switched from a lead-based formulation to a lead-free formulation. This is an example showing the Orbis XRF tool for analyzing hair. Hair, at least in humans anyway, is known to uptake certain metallic elements from the body, famously known for uptaking arsenic metal into the hair. But in analyzing this hair, I found a variety of other trace elements, silicon, potassium, calcium, titanium, zinc. I'm not sure if some of those, I'm going to guess some of these elements are associated with the types of shampoo or conditioner that are used. Hair in general is comprised of a protein keratin, which contains a lot of sulfur. So that's why in the spectrum on the left here, you'll see that the sulfur peak is off scale there at around 2.5 kV. But because the hair grows over time and uptakes certain kinds of elements, you can tell potentially using the hair as you go along the length of it from the root on out when exactly somebody might have been exposed to whatever was taken up in the hair. As I was doing this, I was also wondering whether the same kind of phenomenon might take place in fingernails or toenails. I really can't say, but I just thought it was an interesting possibility. In the United States, there was a problem with the manufacturing of certain kinds of synthetic drugs like methamphetamines using home-based laboratories, where they would manufacture the product at home, let's say in the kitchen, and then go out and sell it on the street. It could be manufactured at home because the various chemicals and reagents to make it could be purchased at the drugstore, and whatever catalysts you need could have been put together from what you can get at a hardware store or drugstore, that sort of thing. So in this particular scenario, it was important if you came across one of these suspected types of drug labs that you would have to test the various chemical residues to demonstrate that you were that the suspect was actually manufacturing the drug. And the Orbis system could be a quick screen for that. So the catalysts involved in making methamphetamines was phosphorus from match heads, and then getting iodine from certain sort of what are those, the antiseptic solutions that you could buy at the drugstore. So this type of analysis is non-destructive. You can do a quick screen of this, and if you need to do something further after that, you can take it and do other sorts of analysis with it. The sample preparation is very simple. Because iodine is corrosive, you want to keep it sandwiched in between two thin X-ray transparent foils of plastic, seal it in between those two plastic foils. And you can get a quick answer on whether there's phosphorus and iodine present in the residues in less than a couple of minutes. And that demonstrates that you have in the residues the various catalytic components involved in the manufacturing process for something like a methamphetamine.